Hello students, welcome back. Welcome to this session on interview guidance. And today's this session is on electromagnetic waves, not complete electromagnetics, where there's a prominent importance for antennas. I did a video on that. I also feel that electromagnetic waves also have a huge role in interviews. The reason is because the electromagnetic waves is used in communications. Electromagnetic waves are the cause of wireless communications, satellite communications, radars, microwave. So a brief idea of electromagnetic waves is always useful for us. So let's look at electromagnetic waves and what sort of questions can be expected. Generally, there is a chance of asking you to write a set of formulas here. They may ask you to write a set of formulas, but I have designed with a few questions where you don't have to write anything. Come out with a few questions where you don't have to write, but also apart from this video, I also expect that you are by hearting all the formulas or knowing all the formulas also, like for propagation constant, intrinsic impedance, or for velocities, for alpha, beta, gamma. You have to know the formulas also. So let's look at the first question. What is a spectrum? The range of frequencies of an electromagnetic wave. Like, what could be the frequency range of electromagnetic waves? They start from a few hertz and go up to 10 power 20, 25 hertz. But they are more stable in their occurrence when it's greater than megahertz, when it's at least 10 power 6 hertz. So from a hertz, few hertz to 10 power 20 hertz, they can exist, but high frequencies, they're more stable. Because in low frequency, the conduction current format exists or the voltage and current format exists. At high frequencies, electromagnetic waves exist. At high frequencies, there is more chance of the electromagnetic wave to be stable because displacement current is frequency dependent. So displacement current, electromagnetic waves or the wireless system is more stable at 10 power 6, 10 power 7 because displacement current has epsilon term. Epsilon is 10 power minus 12. So to overcome that epsilon term, the dou E by dou T should be large. Rate of change with time. I'll be discussing in the next few questions also about this. So high frequencies you find electromagnetic wave to be more stable. But look at the spectrum which goes from 1 to 10 power 25. The lower frequencies, as you can see, there's not much of name given to them. Like there's not much of name because their existence is not very stable. So you can see that at the lower spectrum, you don't really find any name here because their existence itself is tough. These bands. So it's from a few kilohertz, 10 power 3, 10 power 4, you find the radio waves, the TV waves, the wireless TV through broadcast, microwaves at 10 power 9, radar at 10 power 9, 10 power 10, light, the most popular electromagnetic wave because human sensing is through light, human antennas work on light. So 10 power 15 light, X-rays at 10 power 18 to 10 power 20, gamma rays also close to them. Then from here onwards you call them as cosmic rays. So the applications majorly last in the radar and the microwave range. The applications majorly are in this range because the world is slowly going towards microwave. Look at Bluetooth 2.4 gigahertz, Wi-Fi 2.4 gigahertz. Look at cell phone radiation, it's at 1.8 gigahertz. So slowly we are gradually going towards microwave applications, and mostly RF is being replaced. Radio frequency, because of its low frequency and lesser bandwidth, it's being replaced now. I hope this spectrum is clear and their applications are clear. What are the factors that determine the strength of the displacement current? This is exactly what I was discussing in the previous case. Just excuse me. What are the factors that determine the strength of the displacement current? What is displacement current? Wireless energy transfer because of electric field. Wireless energy transfer in the form of electric field. So whenever an electric field is shifting with time, we say there is a displacement current coming. So it's not electron which is moving, but it is electric field which is moving. So it's epsilon dou E by dou T. So electron is moving, we call it as conduction current. Electric field is moving, we call it as displacement current. So it's dou E by dou T. It's not dou Q by dou T or dQ by dt. dQ by dt is conduction current. Now given this dou E by dou T, it's very evident that dou E by dou T means rate of change with time. What is rate of change with time? Frequency. So it comes to be J or I is root minus 1. So I into omega, assuming a harmonic electric field, omega into epsilon into E. So what are the factors that determine the strength of the displacement current? It is frequency dependent, permittivity dependent, and of course the strength of the electric field. So it's permittivity of the medium, electric field strength, and rate of change with time or frequency. That's what decides displacement current. Electromagnetic waves are nothing but a form of displacement current. What are the four factors that determine the propagation aspects of electromagnetic waves? Propagation aspects of electromagnetic waves obviously depend on root of j omega mu into sigma plus j omega epsilon. So they depend on omega, permeability, conductivity, and of course on permittivity. So what are the four factors you should say? It's wave frequency. Frequency of the wave will determine whether the wave can propagate or not. Material conductivity, material permittivity, and of course permeability. So these will combinedly decide whether the wave can travel into that material or not. What is the significance of complex intrinsic impedance? What do you mean by complex intrinsic impedance? Why is that eta is complex? So if you look at it, eta is nothing but E by H ratio. So E by H ratio is coming to be complex. So that means there is a resistance and reactance in that complex term. So impedance is complex means the material has got some resistance and some reactance. So what does this resistance cause? It causes your attenuation. And what does the reactance cause? It causes a phase shift. So it causes a phase shift for the wave to move forward, and this resistance causes some attenuation. So on the whole I can say that material has got resistance and reactance. That's why it is complex. But also there is a significance of why we are getting a complex term after dividing E and H. Because if you look at this E by H division and you are getting some magnitude and phase after that division, that means this E by H division is coming to be complex, giving you a magnitude and phase. What does it mean? It means that there is a delay between the electromagnetic fields. There's a phase delay between the electromagnetic wave propagation. So losses in this attenuation causes delay between E and H maximas. So impedance phase actually signifies this delay. That means E and H are not in phase. Whenever E and H are not in phase, you get a complex eta. So electric field and magnetic field maximas or minimas are not exactly occurring at the same time. They are delayed by some amount. They are no doubt orthogonal. E and H are orthogonal. But being orthogonal, they are not in phase. They have some delays. That is when eta is complex. What is the significance of the term J dot E in an EM wave? What does it signify? Excuse me. What does the term J dot E signify? J dot E signifies the loss, the ohmic power, the loss power or the power that the medium is acquiring because of the loss or the attenuation that is occurring. So ohmic power dissipated in the lossy material in the form of attenuation. That's what is J dot E is. And it will occur only when there is sigma. It will occur only when there is conductivity because J is sigma E. So if somebody asks me what is an ohmic power being lost or what is the loss power, see given this E here, given this E, if it is converting itself into H orthogonally, this is called as E cross H pointing vector or power of the electromagnetic wave. So power of the electromagnetic wave is nothing but product of the E and H. But because of this electric field, if you are getting some electron movement and if you are getting some current in the same direction, that's what is J dot E. Because both are in the same direction. It's cross because they are orthogonal to each other. So J dot E signifies how much of conduction current you are getting and how much of loss it is occurring. Therefore, the amplitude is decreasing progressively. So as soon as the amplitude is decreasing, it is only because of J being produced. So E is producing a J means E is occurring, it's undergoing some loss. And that is because of conductivity, because J is sigma E. So if somebody asks you what is ohmic power, you should say it is the loss power that the material is acquiring because the wave is losing. So wave is losing, material is acquiring, that is what is J dot E. What is the significance of the term E cross H in an electromagnetic wave? Yeah, that's exactly what I told you. It is the power strength, it is the power density of the traveling wave. So how much power that wave is actually carrying per unit area? How much power per unit area that wave is carrying from a small area of that wave? And obviously it is called as Poynting vector, and that's why I call it as strength of the power. More the power per unit area, more is its strength, because strength is always signified by density. Like pressure is nothing but force acting on an area. So smaller the area, larger the force, stronger the pressure. Similarly, power density. These are all the terms you should be understanding about strength. So Poynting vector or E cross H signifies the power strength of the electromagnetic wave. What does the velocity of an EM wave depend in lossless conditions? What does the velocity of an EM wave in lossless conditions depend on? On what factors does it depend on? In lossless conditions, it purely depends on the mu and epsilon terms. If it is lossy, yes, frequency and sigma also will have a role. But otherwise, if it is lossless, it's purely permittivity and permeability dependent. So how much that medium is going to allow electric field, how much that medium is going to allow magnetic field. Only these two will matter for the velocity. So E and H allowing ability is vital here. Which among the three polarizations has a chance of highest loss? It's loss, not lossless. Which among the three polarizations has a chance of highest loss during polarization mismatch? Given that I have a polarization mismatch occurring, which of the three polarization is likely to have a loss? Like let's say I have a circularly polarized wave and I'm putting here a linearly polarized receiving antenna. Then of the two components, I'll surely receive one of them. So polarization loss is 50%. Like suppose I have an elliptically polarized wave with two components and I am putting in linearly polarized wave. I'm having a linearly polarized antenna. And let's say 20% is in one side, 80% is in the other side. So I lose this 20% or I lose this 80%. So there's a chance of losing this depending on the aspect ratio. So circularly polarized wave with 50%, 50% in each direction, there is a chance of losing 50%. Elliptically polarized wave where one can be 80 and the other can be 20, there is a chance of losing even 80%. But if you have a linearly polarized wave, and it is vertical, and your receiving antenna is linearly polarized and it is horizontal, then there is a chance of losing even 100%. So this is what I am trying to express. That whenever you have antennas which are oriented exactly opposite with vertical and horizontal, linear polarization has a chance of maximum mismatch. That's why we use circular and elliptical polarizations. So which among the three polarizations has the chance of highest loss? Obviously it is linear polarization that has the chance. Least always comes with circular polarized or elliptical, because it can be elliptical also because it is depending on aspect ratio. Excuse me. How can we generate a linear polarized wave from a circularly polarized wave? If I've got a circularly polarized wave, how do I get a linearly polarized wave? Very simple. You have to add a left circular and right circular polarizations of equal amplitudes and traveling in the same direction. So just add a left and right circular polarized waves of equal amplitudes traveling in the same direction. Something like this. Look at a left circular polarized wave, for example, with even amplitude sine, E2 amplitude cos in x and y directions. Look at a right circular polarized wave with even amplitude in x and minus E2 out of phase exactly cos term. Because wherever a minus comes in one of the component, left automatically becomes right. So left becomes right because its left is becoming, because a minus is coming here. So add both of them, it becomes simply two even sign, single component. So when you add this left circular and right circular, you'll only get this sine term and this cos will be cancelled. That's so interesting to know that it is going to be single component linearly polarized wave. So whenever you take a left circular and right circular polarized waves of same amplitude and traveling in the same direction, you can always get a linearly polarized wave. This is an excellent example for it. What is a major factor that determines the reflection of an EM wave between two materials? What does the reflection coefficient depend on? It depends on impedance mismatch or the impedance difference of eta 2 and eta 1. So major factor that determines reflection is eta 2 minus eta 1, the impedance difference. If impedance are equal, well, there's no question of any reflection. But if you look at oblique incidence also, I mean, if you look at inclined incidence also, incidence is normal, it's only impedance mismatch dependent. But if you look at inclined incidence, it depends on the difference in the impedance, no doubt, but also on the angle of incidence. It also depends on the wave polarization. Is it S polarized or P polarized? What incident angle is there? Because that will determine your final gamma. Eta 2 cos transmitted minus eta 1 cos incident by eta 2 cos transmitted plus eta 1 cos incident. So incident angle, polarization and difference in the impedances, all the three are vital. What is the difference between critical angle and Brewster angle? Critical angle is a condition for complete reflections or total internal reflection, right? It's one specific angle. So zero reflections is Brewster angle, zero transmissions, complete reflections is critical angle, right? So this is the first thing you should know. So nothing is transmitted, everything is reflected back. Total internal reflection is critical angle, whereas Brewster angle is completely for zero reflections, right, and complete transmissions. Second thing, Brewster angle is for very polarization specific. It is only for P polarized waves, not for S polarization. Whereas critical angle is material specific. It needs to be going from denser medium to rarer medium. Because sine function depends on epsilon 1 and epsilon 2. So if you look at Brewster angle, it's defined by tan Brewster angle is root epsilon 2 by epsilon 1. Whereas if you look at critical angle, it's sine root epsilon 2 by epsilon 1. So here it's mandatory that epsilon 1 should be greater than epsilon 2. Right? So epsilon 1 should be greater than epsilon 2 means you should be going from a denser medium to the rarer medium. That's for critical angle. So that's why I said it's material specific. It depends on material that you are moving from. What is a material with a large loss tangent called as? What material is the one where the loss tangent is very high? I think it's conductor. Conductor is the one which has got a very large loss tangent. Because what is loss tangent? Loss tangent is the ratio of JC by JD. It is sigma by omega epsilon. So obviously conductor is something that has got a large conduction current. So its displacement current or wireless current inside it is zero. Electromagnetic wave cannot travel in a good conductor. So loss tangent is very high for a conductor because electromagnetic waves cannot travel in a conductor. Now, when can the loss tangent be large? Either if the conductivity is large or the frequency is small. So loss tangent is very, very large for a conductor. So it allows voltage and current, but it does not allow electromagnetic waves. So conductor does not allow electromagnetic waves. And it is large loss tangent when the conductivity is large or the frequency is small. That's what I already told you. When the frequency is very, very small, you can't find electromagnetic waves. You will find voltage and current traveling in the conductor. You won't find electromagnetic waves propagating. So that's a common sense. That loss tangent is something that decides depending on conductivity and frequency. So that's all from electromagnetic waves. Further, of course, you can also go through my YouTube videos on electromagnetics interview guidance. There are specifically for electromagnetics, but I hope this should be sufficient for electromagnetic waves. Further, I'll come out with videos next on static fields, transmission lines, and transmission lines and waveguides in one video. Static fields in another complete video. So that electromagnetics is being covered more exhaustively, being my subject. So see you in the next video. Goodbye. Take care.